September 19, 1944, near Aachen, Germany. The rain had not stopped for 3 days. Mud clung to everything. Treads, boots, steel. Inside a camouflaged Panther, Feldwebel Carl Mertens adjusted his rangefinder and watched the distant tree line through periscopic glass slick with drizzle. 2 miles away, Shermans moved hesitantly through the gray morning, their engines muffled under rain. Mertens smiled. He had seen this before. The Americans would come, they would fire, and their shells would bounce like pebbles off cathedral stone. He could almost time it. The faint flash, the rolling delay, the hollow clang of another useless hit. For months, the 75mm Shermans had been punching futility into Panther armor, each round glancing off 80 mm of sloped steel hardened to near perfection. German confidence had become ritual. The Sherman's gun was a joke told in steel and echo. The first American shell struck exactly where expected. Front glacis, 700 malors. A clean spark, no penetrations. Mertens chuckled, calling over the intercom. "Same as always." The loader smirked, already sliding a Pazzi GR-39 round into the breach. The counterfire would come next, and another American tank would join the burned-out carcasses, littering the hedgerows of the west wall. Then something impossible happened. The next flash was brighter, harder, almost blue-white in its glare. The sound that followed was wrong, not the muted clang of deflection, but the blunt concussion of impact and exit. A steel shriek filled the turret as a slug tore through armor once believed invulnerable. The shot punched clean through the Panther's frontal plate, entered at 730 malors, exited through the radio compartment, and vanished into the mist beyond. The crew froze. The gunners stared at the ragged hole the size of a fist. Smoke coiled in strange, lazy spirals. There had been no ricochet, no glancing angle, no chance to react. For the first time since Normandy, a Panther's front armor had been defeated by Sherman. Outside, across the field, the American tank commander didn't cheer. He simply reloaded. The second HVAP round, high-velocity armor-piercing, was already chambered. The tungsten core inside its lightweight aluminum casing made it the fastest 76mm projectile ever fielded by the U.S. Army. At over 1,030 millimeters per second, it didn't deform, it didn't ricochet, it bored through armor like heat through wax. Within minutes, the German position collapsed. 2 more Panthers burned, their crews scrambling out into the mud. One of them, blinded by smoke, shouted that the Americans must be using a new gun. But the barrels were the same length, the turrets unchanged. Only the shells were different, smaller, sharper, impossibly fast. What none of them knew was that the change had not come from the battlefield, but from furnaces and factories thousands of kilometers away. In secret ordnance labs, metallurgists had found a way to turn chemistry into velocity, tungsten into kinetic fire. The result was a round that defied the mathematics of armor and restored to the Sherman what German engineers had stolen: the power to kill at range. By nightfall, American crews were still counting how many they had left. Only 2 HVAP rounds per tank, rationed like gold. Yet in those 2 rounds lay the proof that technology could rewrite fear. The battlefield around Aachen had become the testing ground of an idea born in metallurgy and measured in meters per second. The next question was no longer whether the Shermans could fight back, but how far science and scarcity would let them keep doing it. The story of the Sherman's gun began not on the battlefield, but in blueprints and test ranges. When the M4 rolled off assembly lines in 1942, its 75mm M3 cannon was already a compromise, built for infantry support, not tank duels. It could destroy Panzer IIIs and IVs at moderate range, fire high-explosive rounds with precision, and suppress anti-tank guns. Against armor thicker than 60 millimeters, it was nearly useless. German engineers had leapt ahead, while American doctrine still measured effectiveness in logistics rather than penetration. By 1943, the Wehrmacht's new Panthers and Tigers had redefined what armor meant. Their front plates shrugged off the M3's armor-piercing shells like gravel striking a freight train. The M3 gun, firing the standard APC M61 round, penetrated about 81 mm at 500 meters. The Panther's glacis was 80 mm thick and sloped at 55 degrees, an effective resistance of nearly 150 mm. It was mathematical futility, repeated thousands of times from Normandy to Metz. American ordnance officers had known the limitation long before Europe. In 1942, tests at Aberdeen Proving Ground had already shown that the M3's velocity, 619 meters per second, was too low to defeat modern face-hardened armor. Yet production continued. Replacing or retooling gun mounts across tens of thousands of tanks was seen as disruptive to the war schedule. Doctrine declared that tanks should fight infantry, not other tanks. The assumption was that anti-tank guns and air power would do the killing. That assumption would bleed men from Normandy's hedgerows to the forests of the Ardennes. The response came from a line of blueprints labeled T1E1 and later M1, a 76 mm cannon, longer, sleeker, and capable of far higher muzzle energy. It used the same 76.2 mm caliber as the old 3-inch M7 anti-tank gun, but with a higher pressure chamber and improved recoil mechanism. Early prototypes fired at 792 meters per second, still short of German 75 mm KWK-42 standards, but a significant step forward. At Aberdeen, the M1 punched through 109 mm of homogeneous armor at 100 meters with the standard APC round. On paper, it closed part of the gap. Yet the field reports told another story. When 76 mm armed Shermans reached Normandy in summer 1944, crews found that part of the gap still meant death. The M62 and M79 APC rounds shattered against Panther glacis even at 300 meters. The mathematical comparison was unforgiving. The German 75 mm KWK-42 gun on the Panther fired its PZGAR-3942 projectile at 935 meters per second, capable of 149 mm penetration at 1,000 meters. The American 76 mm M1 managed just 96 mm at the same range. No amount of courage could erase the difference in velocity. The British, with their own Firefly conversion using the 17-pounder, were blunt in assessment. Reports from the Royal Armored Corps described the American 76 as marginally effective against Panther side armor, ineffective against front. In private memos, British ordnance officers joked that Americans fought Panthers by praying for side shots or miracles. They had no idea that the miracle was already being forged in a tungsten furnace in New Jersey. At Aberdeen, engineers under Colonel Gladian M. Barnes were studying the problem in microscopic detail. Armor could not be easily made thicker or stronger. Weight and mobility forbade it. The only alternative was speed. Penetration, they calculated, increased roughly with the square of impact velocity. A projectile striking at 1,000 meters per second delivered nearly twice the kinetic energy of one at 700. If they could raise the velocity without enlarging the gun, the Sherman might stand a chance. They began experimenting with new ammunition types: APCR, armor-piercing composite rigid, rounds used by the Germans, and early American designs under the code T4 and T6. The principle was deceptively simple. Replace part of the heavy steel body with a lightweight alloy, keeping only a dense tungsten core. The lighter mass meant the same propellant charge would accelerate it faster, trading weight for velocity. But making the core survive impact required material harder than anything commonly available. That material was tungsten carbide, gray, heavy, and almost unmachinable. It could pierce steel as if it were wax. The challenge was not theoretical, but logistical. Tungsten was rare. mined primarily in China and Portugal, and both sources were under strain. The Germans had their own supply via occupied territories and Swedish trade routes. America's reserves were limited and already earmarked for machine tools essential to aircraft and ship production. The choice would become a national argument between industry and the Army, cutting tools or killing power. Still, the tests went on. Early T4 rounds left the 76-millimeter barrel at 1,020 meters per second. The effect on armor plates was immediate and shocking. At 600 meters, they penetrated 130 millimeters of homogeneous steel, figures no American tank gun had ever reached. At 100 meters, the penetrations exceeded 170 millimeters, matching the Panther's own gun at point blank. Even British observers admitted that with these new projectiles, the Sherman could defeat any German tank from the side and most from the front at close range. The transformation was real, but the problem had only shifted from physics to production. The Ordnance Department renamed the design the M93 HVAP, high-velocity armor piercing. Each round contained roughly 0.9 kilograms of tungsten carbide, seated in a light aluminum carrier and capped with a hardened steel nose. The complete shell weighed only 6.8 kilograms compared to the standard APC 7.1, but delivered 40% more muzzle energy. In tests at 1,000 meters, it could penetrate 127 millimeters of homogeneous armor, enough to hold a Panther through its gun manlet or lower glacis. The secret was velocity. 1,030 meters per second, faster than any American field gun of the war. Tank crews who saw the demonstration at Aberdeen in late 1943 described it with clinical awe. One HVAP round punched through a 100-millimeter plate, entered the test block behind it, and still carried enough residual velocity to bury itself half a meter into the sand berm beyond. The impact left a perfectly round, clean-edged hole, unlike the ragged tears left by standard rounds. It looked drilled, one ordnance officer noted in his report. It wasn't power, they said. It was precision. Still, skepticism persisted. Colonel John K. Waters of the Armored Force Board argued that the real issue wasn't gun performance but ammunition supply. Without enough rounds, the improvement was academic. Ordnance replied with quiet numbers. If they could secure 500 tons of tungsten annually, they could equip every 76-millimeter Sherman with 2 HVAP rounds per day of combat. The math was cruelly efficient, but the decision was clear. The future of the Sherman lay not in heavier guns, but in faster projectiles. By autumn 1944, limited shipments of HVAP rounds reached depots in England and France. Each box carried a yellow label marked for 76-millimeter M1 series HVAP M93. Tankers uncrated them with curiosity, reading the stenciled muzzle velocity, 3,400 feet per second, 1,036 meters. Most had never seen a number that high outside aircraft speeds. In field briefings, ordnance officers warned crews to aim carefully. The new rounds flew flatter, struck faster, and could ricochet dangerously if mishandled. They called them super shot. On paper, the gun was still the same M1A1 or M1A2 barrel, 57 calibers long, rifled for stability. But the physics had changed. The energy leaving that barrel had increased by a third, the time of flight cut by half. The 76-millimeter M1 with HVAP was no longer a supporting weapon, it was a predator. What began as a mathematical curiosity in a laboratory would soon become the invisible edge between life and death inside the tank turrets of Western Europe. The weapon was ready. The question that remained was whether the United States had enough tungsten and enough time to turn laboratory success into battlefield salvation. The new round had solved the equation of speed, but it had opened another, one measured not in meters per second, but in kilograms of tungsten. Every HVAP projectile demanded a dense core cut from metal rarer than gold. The United States possessed little of it. Before the war, the nation produced barely 1,200 tons a year, most of it consumed by the machine tool industry. Yet tungsten was now the key to both cutting steel and piercing it. In 1940, American engineers had learned that the same carbide that made lathe bits stay sharp could also defeat armor. The discovery created a quiet, strategic crisis. Tungsten's melting point, 3,122 Du, made it ideal for cutting hard alloys used in tanks, guns, and aircraft engines. Every factory that machined steel relied on tungsten carbide tools. Without it, production slowed to a crawl. To divert tungsten from factories to ammunition was to gamble with the entire war industry. Supply came from narrow threads on the map. Portugal's Panther-Killers mines provided about 35% of the world's ore. China, still fighting Japan, produced another 30%, mined by hand in the mountains of Jiangxi and Hunan. Both sources were unstable, one neutral, the other under siege. Germany, through occupied France and deals with Sweden and Spain, controlled most of what remained. By 1943, Allied intelligence estimated the Reich was importing 3,000 tons a year. America imported less than half that amount and was already rationing. Inside Washington's War Production Board, the debate became mathematical. The Ordnance Department demanded 500 tons of tungsten for HVAP cores. The machine tools section warned that such diversion would cut aircraft engine output by 15% within months. Every ton of tungsten carbide could make either 10,000 cutting inserts or 40,000 anti-tank penetrators, not both. In December 1943, the conflict reached the President's Science Advisory Committee. The conclusion was reluctant. Priority to production tools. A tank gun without a tank factory is useless. Still, experiments continued. At the Bethlehem Steel Metallurgical Laboratories, chemists devised methods to recover tungsten from worn cutting tools, dissolving carbide in molten sodium carbonate and reprecipitating pure oxide. Across the country, scrap drives quietly added hard metal bins alongside rubber and aluminum. Each kilogram reclaimed meant more potential HVAP cores. Children gathered broken drill bits as if collecting ammunition. The hidden front of the tungsten war ran through foundries, not trenches. Portugal's neutrality became suddenly valuable. In 1943, American and British diplomats, acting through the Luso-American Tungsten Agreement, purchased the entire output of the Panther-Killers mines at fixed prices. Gold flowed into Lisbon, and ore flowed out through Atlantic convoys. German agents attempted to bid higher, sending submarines to intercept shipments. The contest for metal became a miniature arms race within a larger one. Each intercepted freighter could change hundreds of tank duels months later. Meanwhile, American scientists explored substitutes. The National Bureau of Standards tested molybdenum, vanadium, even depleted uranium alloys. None matched tungsten's density or hardness. At 19.3 grams per cubic centimeter, only depleted uranium came close, but it was radioactive and scarce. The physics of penetration remained uncompromising. Density multiplied by velocity, divided by sectional area. Tungsten alone gave the numbers that mattered. By spring 1944, U.S. tungsten stockpiles were calculated in days of supply. The War Production Board created a classification system: critical, essential, non-essential. HVAP ammunition received a critical rating, but only for limited issue. Production contracts went to the Remington Arms plant in Bridgeport and the Chrysler Tank Arsenal in Detroit, both re-equipped with carbide sintering furnaces capable of 1,600 Dirk. Each furnace produced barely enough cores for 200 rounds per shift. The M93 round became a precision instrument built by a mass production nation. Germany faced its own scarcity. The Reich's tungsten imports had peaked in 1942, then collapsed under Allied blockade. Swedish exports slowed. Portuguese shipments ceased after Allied diplomacy tightened controls, and Chinese mines were lost to Japanese advance. The German answer was compromise. Replace tungsten in machine tools with inferior steel alloys, slow production, and save what little remained for anti-tank ammunition. By late 1944, even the vaunted Pezzi GR-40 rounds for Panther and Tiger guns were rationed, issued only to elite units and aces. Tungsten starvation was global. Within American factories, the balance of necessity and invention took physical form. At Remington, workers in heat-resistant gloves poured powdered tungsten carbide into graphite molds, sintered it under hydrogen, then pressed it into aluminum sabots, machined to thousandths of an inch. Each finished core passed through magnetic testing to ensure uniform density. Waste was measured in grams, not kilograms. The process was so exact that a single, defective batch could halt production for a week. The weapon that seemed simple on paper required industrial perfection. In Detroit, Chrysler engineers designed assembly jigs that aligned the tungsten core within the aluminum body using optical comparators borrowed from the watch industry. Tolerances of 0.05 millimeters ensured the projectile would fly true at 1,000 meters per second. Even microscopic imbalance could tear the shell apart in flight. HVAP rounds were thus less a bullet than a miniature machine tool, each one a product of the same precision culture that built aircraft engines and radar systems. Numbers remained stark. Through 1944, American factories produced roughly 25,000 HVAP rounds per month, less than a single day's consumption of standard 76 MiG ammunition in heavy combat. Most tank battalions received a handful of crates, 2 rounds per gun, sometimes less. Commanders logged their use with bureaucratic precision, noting target type, range, and result. The data returned to Washington like laboratory reports from the field. Every impact was another experiment in applied physics. In this new arithmetic of war, tungsten became more than a metal. It became a measure of civilization's reach. The Allied ability to mine, refine, transport, and weaponize it determined which tanks survived the next encounter. Behind every burst of flame on the Western Front lay an invisible network of contracts, freighters, furnaces, and men who had never seen a battlefield. The material war was fought by chemists and accountants as surely as by soldiers. By autumn 1944, American officers could trace the path of a single HVAP round from Mountain Ore in Portugal to the muzzle of a Sherman near Aachen, a journey of 8,000 kilometers, compressed into weeks by ships, trains, and assembly lines. It was industrial choreography set to the rhythm of logistics and need. What emerged from that chain was not just a projectile, but proof that material science had become strategy. The balance between scarcity and invention had found its weapon. What remained was to test whether those few kilograms of tungsten could alter the mathematics of battle itself. The weapon took shape not in a single laboratory, but across a chain of workshops, stretching from New Jersey to Illinois. At the Frankfurt Arsenal, metallurgists measured the density of tungsten carbide grains under microscopes meant for jewelry. At Watervliet, artillery engineers tested new propellant formulas that burned hotter and faster without cracking gun barrels. The project moved forward under the Ordnance Committee designation Armor-Piercing Composite Rigid, T4E, later renamed M93 HVAP. Each document bore the same warning in red ink. Confidential. Projectile development for 76 mm gun M1 series. The design principle was brutally simple. Replace the heavy steel body of a conventional shell with a lightweight aluminum shell carrier. Place within it a tungsten carbide penetrator, dense and narrow, held by a steel nose cap and copper driving band. When fired, the aluminum sabot provided the necessary bore fit and spin stabilization. Once it struck armor, the tungsten core alone did the killing. The result was speed, unprecedented for a medium-caliber tank gun. Test data from Aberdeen in February 1944 recorded a muzzle velocity of 1,036 meters per second using the standard M62 propellant charge. The projectile weighed 6.8 kilograms, 300 grams lighter than standard ammunition, yet carried 40% more kinetic energy. Against homogeneous armor, it achieved 127 millimeters of penetration at 1,000 meters, 178 millimeters at 100 meters. On the test range, the plates didn't bend or crack. They vaporized where the core struck. Observers described a small flash, a dull metallic thud, then a hole as clean as a drill press. But field ammunition is never laboratory perfect. Engineers quickly discovered that at such high velocities, even microscopic imbalance could cause yaw or disintegration in flight. To survive the acceleration, the tungsten core had to be perfectly centered within its aluminum shell, tolerances below 0.05 of a millimeter. Optical alignment rigs borrowed from the watchmaking industry were installed at Remington's Bridgeport plant to ensure consistency. Each round was weighed, measured, and fired for proof before mass issue. The level of precision bordered on obsessive. Failure meant not a defective bullet, but a destroyed gun and dead crew. By late spring 1944, small batches reached the proving grounds of Camp Hood, Texas, for troop training. Tank crews from the 2nd Armored Division watched as instructors fired HVAP rounds at captured Panther hulls shipped from France. The results silenced the range. At 800 meters, one round penetrated the glacis, passed through the transmission housing, and struck the ground behind with enough velocity to ricochet skyward. Crews reported that the impact sounded different, sharper, metallic, final. "It doesn't hit," one gunner wrote in his log. "It goes through." The news spread quietly through armored units. In maintenance depots and forward ordnance companies, men began to hoard the new rounds, marking them with chalk crosses or taping the tips with cloth. To the tankers who had seen Panthers shrug off dozens of standard hits, the M93 was a talisman. A single round could change the outcome of an ambush. It was power concentrated into one shot, reserved for when survival demanded certainty. Yet production lagged behind expectation. Each tungsten core required complex sintering at over 1,500 degree Kelvin, and factory throughput never exceeded 25,000 rounds per month. By summer 1944, demand from Europe exceeded supply tenfold. Commanders issued strict orders: 2 HVAP rounds per tank per day of combat, to be expended only against heavy armor. Reports from France confirmed the practice. A tank commander of the 32nd Armored Regiment wrote, "We carried 70 rounds per gun, 2 marked silver tip. Those were for Tigers. We never wasted them." Combat testing began in earnest during August 1944 in the hedgerows of Normandy and the approaches to the Siegfried Line. The first confirmed kill by HVAP came near Saint-Lô when a 76mm Sherman from the 4th Armored Division engaged a Panther at 700 meters. The gunner's after-action report described a single flash, a plume of smoke, and the German tank erupting seconds later. Inspectors later found the entry hole in the lower glacis, perfectly round, 7 centimeters wide, burned smooth. "Penetration complete. Crew likely killed instantly," the report read. The myth of Panther invulnerability had met its counterweight. Field evaluations soon followed. Colonel Gladian Barnes, the chief of the Ordnance Department's Development Branch summarized the findings in October 1944. M93 provides decisive advantage within 800 yards. Accuracy excellent. Penetration exceeds requirement. Limitation: scarcity of core material. He pushed for expanded tungsten allocation, citing combat necessity. The War Production Board, already rationing the element between aircraft toolmakers and armament factories, approved modest increases. By December, shipments had doubled, but still covered only a fraction of the need. In battlefield photographs from late 1944, the difference is barely visible. A 76-millimeter round with a slightly shorter casing, a darker tip, a stenciled mark reading HVAP M93. Yet inside that modest shape lay decades of metallurgy and logistics. Soldiers often didn't know the chemistry or the science. They only knew the result. When the round struck, it made a sound distinct from any other shell. A sharp crack, then silence, then a pillar of smoke from the target that didn't stop burning. German field analysts noticed too. Reports intercepted by Allied intelligence mentioned unidentified new U.S. shell with abnormally high velocity and penetration through upper front armor. Some units suspected a new gun entirely. Others blamed faulty steel in their own tanks. The truth, an aluminum casing and a tungsten heart, remained classified. To the crews who used it, the round felt almost unfair, a quiet correction of 2 years of disadvantage. By winter, HVAP had become the whispered equalizer in every armored regiment from Lorraine to the Ardennes. A handful of silver-tipped rounds in each turret represented the line between desperation and dominance. Behind every shot stood the invisible machinery of a continent. Mines, furnaces, railways, ships, all converging into that single instant of impact. The birth of HVAP was complete. What remained was its baptism under fire, where scarcity, velocity, and necessity would converge to decide how much difference tungsten could truly make. The first shipments of M93 HVAP arrived in Europe in late August 1944, just as Allied armor approached the German frontier. In wooden crates marked restricted tungsten ammunition, the silver-tipped rounds were distributed to the 2nd and 3rd Armored Divisions. Each tank received 2 to 4. They were stored separately, issued by name, signed out like gold. Crews joked that they carried more paperwork than propellant. At first, few officers believed the claims. In the hedgerows of Normandy, Sherman crews had already learned fatal caution. Their 76-millimeter guns could destroy Panzer V's and Stooges, but against Panthers, the front armor remained inviolable. Commanders ordered the new rounds tested under real conditions. On September 5th, near Mons, Belgium, a Sherman of the 33rd Armored engaged a Panther at 600 meters. The gunner fired 1 HVAP round. The Panther's front plate split, its engine erupted, and the tank burned within seconds. The crew's report was 2 lines long: penetrated, complete kill. The word spread faster than official bulletins. By mid-September, U.S. ordnance officers tracked 63 confirmed HVAP kills, most against Panthers previously immune to fire. The Germans noted them as hits from new type shell. To the Americans, they were proof that physics had finally caught up with belief. In every after-action report, tankers wrote the same line: no ricochet. The effect was not just destruction, but psychological reversal. Crews who had once feared Panther silhouettes now hunted them. Supply never matched demand. Each combat unit received an allotment based on tungsten availability, approximately 1 round per tank per day of engagement. At battalion briefings, platoon leaders marked their ammunition charts in red for HVAP. Those 2 symbols on paper represented their best chance of survival. Tank loadouts were precise: 70 rounds total, 30 HE, 38 AP, 2 HVAP. The M93s were kept separate, wrapped in canvas to prevent identification by enemy observers. The first large-scale use came around Aachen in October 1944. The urban terrain favored ambushes. Panthers and tigers waited at street corners, their guns covering avenues of fire. American tanks approached slowly, using smoke and radio coordination. When the moment came, gunners selected their silver-tipped rounds. Reports from the 2nd Armored Division recorded penetrations through gun mantlets and lower hulls at ranges previously impossible. In one day, 5 Panthers were knocked out by direct frontal shots. German commanders, convinced the Americans had mounted a new high-velocity gun, ordered investigations into captured wrecks. They found nothing new, except holes. For tankers in the field, HVAP changed tactics. Where the old rule was flanking, the new was confidence. Crews learned to wait for the perfect moment. 1 shot per enemy, calculated and cold. A Panther spotted across a village square was no longer a death sentence, but a problem to be solved with mathematics, range, angle, velocity. If they fired first, the battle was over. For the first time since Normandy, American crews felt the balance tilt in their favor. German intelligence attempted to explain the change. Field reports from the 116th Panzer Division near Geilenkirchen described perforations through front plate at 500 meters by unknown caliber. Some engineers suspected a new British sabot round. Others blamed defective steel. Laboratory tests on captured fragments revealed traces of tungsten carbide. WA-Proof 6, the German Weapons Testing Office, issued a confidential bulletin warning that Allied forces employ light-cased projectile with hard core of unusual density. Their recommendation: increase armor hardness. The factories, already crippled by bombing and alloy shortages, could not comply. For the men using it, the HVAP round was less a scientific achievement than a ritual. They cleaned its surface until the metal shone, loaded it slowly, spoke less. When it left the barrel, there was a distinct sound, a sharper crack, a shorter echo. Observers said the round looked like a tracer made of light. In after-action reports, gunners wrote not of emotion, but numbers, range, angle, time to impact. The language of war had become pure ballistics. The limitation remained scarcity. By November, requests for resupply exceeded production 5-1. Tank battalions shared their stock through unofficial barter: 2 HVAPs for a spare radio, 1 for fuel from another company. Every round was accounted for, logged, and signed. Each time a tank fired one, the crew recorded the result in their daily report so ordnance could justify more. The rounds became currency, exchanged in mud and danger. As the front moved into the Hürtgen forest and then the Ardennes, the impact of HVAP could be measured in German tactics. Panther commanders no longer held positions confidently. They turned their tanks sideways behind cover, angling their armor to avoid frontal hits. Reports from the 5th Panzer Army spoke of new American ammunition rendering front plate unsafe. The illusion of immunity was gone. The Germans had spent years building machines to dominate by armor. Now a handful of small, fast bullets were undoing that philosophy. By the end of 1944, roughly 100,000 M93 rounds had been shipped to the European theater. Most were fired between Aachen and the Rhine. Their effectiveness could be read in field statistics, where standard APC rounds achieved 10% kills per engagement. HVAP averaged 47%. Each shot cost the war machine more than a jeep, but no one complained. Velocity had become currency, and every penetration was worth the price. For Berlin's analysts, the lesson was clear, but too late. Speed had become the new armor. And as American crews prepared for the final push toward the Rhine, they carried those 2 silver-tipped rounds, not as hope, but as proof that the balance of the tank war had finally changed. The reaction in Germany would come soon after, when frontline reports of shattered Panthers reached the offices of Wehrmacht engineers still believing in invulnerability. The first reports reached Berlin in October 1944. At Wehrproof 6, the German Army's Weapons Testing Division, officers reviewed fragments from destroyed Panthers collected near Aachen. The data defied explanation. Penetrations through 80mm frontal plates at ranges beyond 600 meters. Clean holes, round and sharp-edged, with no spalling typical of conventional hits. Metallurgists examined the inner surfaces and found traces of tungsten carbide. One memo from October 27th read, "Enemy projectile exhibits composite structure, light casing, dense core, velocity estimated over $1,000 ms." For German engineers, the conclusion was impossible. Only high-velocity, long-barrel guns, such as their own KW-K42, could generate such impact. Yet captured American tanks showed the same M1A1 barrels as before. Intelligence officers speculated that the Allies had developed a secret propellant or sabot system. Others dismissed the evidence as coincidence. Steel fatigue, one analyst wrote, or defective plate. But field data kept accumulating, and excuses became harder to sustain. Frontline units were the first to understand the change. Tank commanders reported Panthers knocked out by direct frontal hits from Shermans. At Stolberg, a Tiger, I was penetrated through the gun mantlet at 700 meters, killing the crew instantly. Investigators sent armor samples to Kummersdorf for analysis. Results confirmed that the steel met full specifications. The failure had come not from metallurgy, but from physics. A projectile had exceeded the limits of design. In November, Wehrproof 6 issued an internal alert. The document classified the new ammunition as U.S. Special Armor Piercing, tungsten-cored, and warned that existing Panther armor could no longer be considered invulnerable. The notice reached Panzer brigades by December, accompanied by an instruction to avoid frontal engagements within 800 meters when facing 76mm Shermans. On the battlefield, that meant retreating before firing range, something no Panther crew had been trained to do. The discovery triggered debates within the German armaments ministry. Some called for thicker plates, others demanded urgent research into improved face-hardening techniques. Both solutions were fantasy. The Ruhr's steel mills were already operating on emergency alloys short of nickel, molybdenum, and vanadium. Even maintaining existing armor quality was nearly impossible under Allied bombing. The tungsten problem made it worse. Germany's own HVAP 40 ammunition, the counterpart to HV, had disappeared from the front by mid-1944, sacrificed to industrial shortages. The irony was bitter. The Reich had pioneered tungsten-cored shells, then lost the ability to produce them. German crews noticed the change long before headquarters did. "The Americans have found the answer in speed," wrote Oberleutnant Ernst Faber of the 2nd Panzer Regiment in his diary. His Panther was destroyed near Geilenkirchen by what he described as a small, shrieking projectile that went through like lightning. Another officer, Hauptmann Helmut Keller, told interrogators after the war that his men had begun calling the new ammunition Blitzkern, lightning core. To them, it was a ghost weapon, unseen, unfought, lethal. Wehrproof 6 ordered reverse engineering of captured American rounds. In January 1945, samples of M93 HVAP arrived at the Hillersleben test range. Analysis confirmed the American approach: an aluminum casing, a tungsten carbide penetrator, steel cap, copper driving band. No new propellant, no new gun, only precision manufacturing and abundant material. "The Americans use our concept," a German engineer noted bitterly, "but with better industry." The report circulated quietly through the armaments ministry. It was an autopsy written in metallurgy. By then, the problem had moved beyond engineering. The German economy could no longer supply tungsten in meaningful quantities. Portuguese shipments had ceased, Chinese mines were inaccessible, captured stocks were exhausted. Attempts to substitute hardened steel cores failed under test conditions. The penetration dropped by half, and the round shattered on impact. Germany's industrial miracle had reached its chemical limit. In the field, tank crews adapted through improvisation. Panther commanders angled hulls sharply, firing from the partial cover, avoiding duels. Orders emphasized ambush and range advantage. Yet even these measures eroded under American coordination and radio control. Every new encounter risked exposure to the silver-tipped rounds that seemed to ignore armor. The psychological toll was profound. After years of supremacy, German tank crews felt hunted. By February 1945, captured diaries revealed the shift in tone. "Our armor is no longer certain," wrote Lieutenant Dieter Meinhof. "They shoot through us like through air." The myth of invulnerability, the faith that had sustained the Panzerwaffe since 1940, was dissolving under mathematics and scarcity. The tungsten duel had ended before it was fully understood. What remained was a war of production, one side constrained by collapse, the other by abundance. And in that imbalance lay the true power of the American weapon system, industry itself, converting chemistry into dominance. The advantage of tungsten could only last as long as industry could feed it. In late 1944, the War Production Board reorganized the nation's entire tungsten allocation under Program W-107, designating HVAP ammunition as a Class A priority, equal to aircraft engines and radar equipment. The order redirected ore from civilian machine tool factories to ordnance plants. Production targets were exact: 25,000 rounds per month by November, 40,000 by January 1945. Each finished round consumed 0.9 kilograms of tungsten carbide. No substitutions, no reserves. The arithmetic was ruthless. At Bethlehem Steel's subsidiary in Baltimore, the new furnaces burned day and night. Powdered tungsten carbide, imported through convoys from Lisbon, was pressed into cores by hydraulic dies operating at 1,500 kilograms per square centimeter. Each furnace batch yielded only a few hundred usable penetrators. Waste was recovered, crushed, and melted again. Nothing was discarded. The material was too rare for error. Remington's Bridgeport facility machined the aluminum sabots, while Chrysler's Detroit tank arsenal assembled complete rounds for shipment. Every plant ran 3 shifts, 7 days a week. Precision replaced quantity as the measure of victory. Factories operated like clockworks of electricity and fire. Conveyor belts carried trays of shining cores through hydrogen furnaces glowing orange. Technicians in asbestos gloves rotated molds by hand, aligning each penetrator before quenching. The air smelled of graphite and hot metal. Supervisors checked tolerances with micrometers, reading to a 10,000th of an inch. A single flawed round meant lost tungsten and wasted man-hours. The process had become as exacting as aircraft manufacturing. Each M93 was effectively handmade by 1,000 machines. The cost was enormous. Standard armor-piercing shells cost less than $10 apiece. HVAP exceeded $60. Yet no one questioned the expense. Ordnance officers calculated that each Panther destroyed offset the cost of 300 shells. Efficiency had become a form of morality. Whatever struck cleanly was worth its weight in tungsten. Shipping records reflected the scale. Rail cars labeled ammunition, special alloy, 76 mm, left Detroit daily, bound for the ports of New York and Baltimore, then across the Atlantic under armed escort. American logistics transformed the rare metal into a weapon system. The Army Transportation Corps designed insulated containers to protect the delicate aluminum cases from salt corrosion. Each crate held 25 rounds. Each ship carried 50,000. Within 60 days of leaving the mine in Portugal, the metal reached a tank crew in Belgium. The global loop of extraction, refinement, assembly, and delivery had become the true battlefield. Statistically, the numbers told their own story. Between September 1944 and April 1945, U.S. industry produced roughly 220,000 HVAP rounds for 76 mm guns, 70,000 for 90 mm, and 18,000 for tank destroyers. Total tungsten consumed, 2,400 tons, nearly the entire Allied supply. In comparison, German production of tungsten-cored ammunition during the same period fell below 15,000 rounds. The disparity wasn't just quantitative, it was systemic. America could afford precision because it could manufacture abundance everywhere else. Behind every shipment stood invisible armies of engineers and clerks. The Bureau of Mines tracked ore tonnage by the hour. The Office of Defense Transportation calculated ship loading times, rail car turnover, and fuel costs. The National Bureau of Standards verified metallurgical specifications for every lot of carbide. Coordination was digital before the digital age. Paper, telegraph, telephone. Every schedule met another, every component synchronized. The HVAP project was less a weapon than a demonstration of how organized matter could conquer chaos. For the soldiers who received the crates, none of this was visible. To them, the silver-tipped round simply appeared, sealed, numbered, ready. But the invisible labor behind them defined the modern war. Factories in 23 states contributed parts. Mines in 4 continents fed the furnaces. Each HVAP round represented an international alliance condensed into a single kilogram of metal, traveling at 1,000 meters per second. When American production peaked in early 1945, observers at the War Production Board compared the figures to pre-war Germany's total tungsten imports. 1 month of Allied manufacturing equaled the Reich's entire yearly capacity. The balance was irreversible. In the same way that radar had conquered night, industry had conquered scarcity. The tungsten bottleneck that had once threatened the program was now a proof of scale, a demonstration that logistical power could turn even rare elements into mass weapons. At Bethlehem Steel, an engineer noted in his logbook, "We are not making ammunition, we are manufacturing velocity." The phrase captured the essence of the system. Every round was a small piece of kinetic infrastructure, built by layers of electricity, chemistry, and organization. In a war defined by tons of steel and hours of flight, America had found a new metric, meters per second. By spring, as the Rhine crossings began, the factories that had built the M93 were already shifting toward post-war contracts. Tungsten remained scarce, but its secret had been proven. Speed could be industrialized. And while the last Panthers burned on the Western Front, new freight trains carried the same metal toward the Pacific, where its lessons would soon be tested again under different skies. The ultimate validation came not from laboratories or factories, but from battlefields, frozen under winter rain. February 1945, near Elsdorf, west of Cologne. The 3rd Armored Division advanced along the highway, its Shermans stretched in column through smoke and fog. Ahead, 2 Panther tanks of the 9th Panzer Regiment blocked the road, hulls angled, guns elevated. For months, such an encounter had meant destruction. This time, it lasted less than 30 seconds. Sergeant Bob Early's 76 mm Sherman halted behind a wrecked half-track. The gunner adjusted elevation to 720 meters. "Silver tip," he ordered. The loader slammed the M93 round into the breach. The crack that followed echoed off the stone walls. The tungsten core struck the Panther's front plate just below the gun mantle. passed through the crew compartment, and exited through the engine deck. The tank burned before it could fire. A second HVAP round disabled the second Panther through the lower glasses. The entire engagement recorded 1 minute, 43 seconds. The after-action report concluded, HVAP, satisfactory performance, penetration complete. Within weeks, similar reports arrived from every sector. At Linnich, a single Sherman of the 743rd Tank Battalion destroyed 3 Panthers in sequence. At Pruim, gunners noted penetrations at over 900 meters. The Ordnance Department collected the field data and compiled statistical summaries. When firing standard M62 armor-piercing ammunition, Sherman units achieved a 10% frontal kill ratio against Panthers. With HVAP, the ratio exceeded 45%. The numbers required no interpretation. Photographs taken by battlefield analysts show the evidence. Clean entry holes, circular and smooth, the steel edges fused by heat. Unlike the ragged tiers of previous hits, HVAP impacts resembled machining operations. Armor was no longer shattered, it was cut. The Germans had designed their tanks to defeat mass. They had not designed them to defeat precision. Tank crews quickly adapted their tactics. With limited HVAP rounds, each shot had to count. Crews learned to target the turret ring, the lower glasses, the junction of plate and weld, structural weak points invisible to the untrained eye. Gunnery manuals were updated to include exact ranges and penetration angles for M93 ammunition. 2 rounds, 1 kill, became an informal rule among veteran gunners. The battlefield became a contest of measurement, distance, angle, time. The psychological impact matched the physical. Crews who had once spoken of survival now spoke of certainty. The HVAP round had removed hesitation from combat. Gunners no longer needed to maneuver for flanking positions. They engaged head-on, trusting velocity over armor. Tank commanders described engagements measured in seconds, where a single silver flash decided the outcome. Speed had replaced mass as the arbiter of survival. German records confirmed the shift. Reports from the 9th Panzer Division, dated March 3, 1945, mention Allied tanks with greatly increased armor penetration, possibly new high-energy projectile. Interrogations of captured officers after the war revealed disbelief turning to resignation. One Panther commander told U.S. interrogators, "We saw Shermans killing us from the front. We thought it was a new gun. It was the same gun, but faster." The explanation was accurate enough. American ordnance teams studied the recovered wrecks. At Ellsdorf, engineers measured entry points and thicknesses, correlating results with field reports. The average penetration depth exceeded expectations by 12%. Even sloped armor at 55 degrees yielded to the tungsten cores at close range. Temperature and material fatigue made little difference. The round's density and velocity simply overwhelmed the steel's capacity to absorb energy. Combat footage from the Rhine crossings in March 1945 captures the transformation. Shermans advanced through shattered towns, their guns firing in short, deliberate rhythm. Each shot strikes, flashes, ends in smoke. Behind the numbers, a new kind of warfare had emerged. Industrial precision applied to destruction. Every HVAP round represented a network of factories, furnaces, and laboratories condensed into one moment of impact. By April, the 76mm Sherman's reputation had changed entirely. German prisoners no longer called it the Ronsen. They called it the Schneller-Tod, the fast death. Its gun, once mocked, now carried the authority of inevitability. The tungsten cores, produced in distant furnaces and carried through convoys and depots, had rewritten the equation of tank warfare. In those final months, the 76mm HVAP had proven not just its design, but its doctrine. that intelligence, coordination, and velocity could replace brute force. The last phase of the war would confirm the same lesson on a larger scale, when production numbers, not calibers, decided what survived. The war ended before the tungsten did. When the guns fell silent in May 1945, thousands of M93 HVAP rounds still sat in ammunition depots from Antwerp to Le Havre. Their crates were marked for return, not use. The tankers who had guarded them as treasure now watched trains haul the rounds away to storage yards. The urgency that had filled every day of 1944 dissolved into the arithmetic of victory. At Aberdeen, engineers dismantled the spent casings returned from Europe. They examined impacts under microscopes, measuring microfractures, melting zones, and heat signatures. The reports confirmed what the battlefield had shown. Tungsten cores had remained structurally intact even after penetrating armor 3 times thicker than their own diameter. The data were clinical: penetration angle, OCOS 0 plus 2 degrees, residual velocity, 220 memoes. What had begun as a field experiment ended as a solved equation. The Ordnance Department's post-war summary, report number T27A46, concluded, the 76mm HVAP M93 proved effective within 800 yards against all known German armored types. Limitations, scarcity of core material, high production cost, logistic complexity. The statement was bureaucratic understatement. On the battlefield, the weapon had changed doctrine. Tank gunnery had shifted from volume to precision, from weight to speed. The lesson would persist far longer than the round itself. Factories that once forged penetrators now prepared for peacetime contracts. The tungsten furnaces at Bridgeport cooled for the first time in 18 months. Engineers recalibrated their presses to manufacture drill bits, not ammunition. Yet even in demobilization, the technology refused to die. By 1946, new designs emerged. APDS, armor-piercing discarding sabot, firing even smaller tungsten cores at higher velocities. The British 17-pounder became the test platform. The Americans followed with 90mm and 105mm experimental guns. The M93 had been proof of concept. The physics of speed had replaced the mythology of armor. Post-war analyses compared the Panther's 80mm glacis to a 25mm tungsten rod at 1,000 Newton-meters. The result was always the same. Energy won. Steel could be hardened, sloped, layered, but the mathematics remained one-sided. The future belonged to velocity. Designers across nations, Soviet, British, American, accepted the new logic. Every generation of tank that followed carried it forward. Thinner armor, faster rounds, greater range. Tungsten itself became a strategic mineral of the atomic age. In 1947, the United States established the Defense National Stockpile, holding 50,000 tons of tungsten ore in sealed vaults. The memory of wartime scarcity had turned into policy. Reports warned that future wars would again be decided by metals mined in mountains most citizens would never see. The industrial race for velocity continued, only now measured in megajoules instead of meters per second. Within the U.S. Army, the legacy of HVAP was institutional. Training manuals rewrote the language of tank gunnery. Terms like strike angle, impact energy, and core density replaced armor thickness. Ballistics tables became as important as tactics. What soldiers had called silver tip became an entire class of munitions. The transition to APDS and later APFSDS, armor-piercing, fin-stabilized, discarding sabot, followed a straight line from those first M93 shells fired near Aachen. For ordnance engineers, the war's end was only an intermission. They studied German and British developments, copied useful elements, and refined American metallurgy. By the early 1950s, depleted uranium began replacing tungsten in test programs, not because it was superior, but because it was plentiful. The same arguments replayed. industry versus weapon, production versus power. The HVAP story had become the template for every future decision where science met logistics. Historians later called it a minor technical innovation, but those who understood production disagreed. The M93 was the moment when America proved that engineering could move faster than ideology. The Panther had represented the peak of traditional armor philosophy: mass, thickness, deflection. The HVAP round showed that such faith could be undone by chemistry, computation, and organized supply. Every later conflict, from Korea to the Persian Gulf, would follow the same logic. The side that controlled material flow would control the battlefield. In Germany, post-war analysts studying captured reports recognized the pattern. A Bundeswehr training manual of 1959 stated, "The defeat of superior German tanks by inferior American vehicles with superior ammunition and communications demonstrates that information and velocity outweigh mass." It was a line written without sentiment, derived from burned steel and measured holes. For the men who had fired the rounds, the memory stayed mechanical. They described the sound more than the feeling: a sharp crack, the brief silence before impact, the smell of hot oil and burnt paint. No celebration, no triumph, just confirmation that the equation worked. Their diaries read like maintenance logs: temperature, distance, penetration, result. In a war saturated with emotion, the tungsten rounds remained purely factual. By 1948, most of the remaining HVAP shells were melted down. The tungsten was reclaimed for cutting tools, the aluminum recycled into aircraft frames. Nothing of the weapon survived except the data and the doctrine. Even the Shermans that had fired them were sold as surplus, their guns cold, their radios silent. Yet, inside every modern kinetic penetrator, the long rods fired by M1 Abrams, Leopards, and T-90s, exists the same geometry first proven by the M93. The lineage is metallic, not sentimental. Historians often describe wars as contests of courage or strategy. The tungsten story suggests something else: a contest of refinement. The victory did not come from thicker armor or larger guns, but from tolerance measured in hundredths of a millimeter, from furnaces that held temperature within 10 degrees, from miners pulling gray ore from the dark rock halfway around the world. The decisive battlefield was the factory floor. When the archives closed, the numbers remain: 1 kilogram of tungsten, 1 aluminum shell, 1 second of flight. That was enough to overturn the equations of armor that Europe had believed immutable. Velocity had replaced faith, and in that transformation, from steel to tungsten, from weight to speed, modern war found its final language: precision without mercy.